Hi guys, sound check.
We could hear you.
Could you repeat? I'll adjust volume here.
We could hear you.
Okay, thank you. Okay, I believe it's time to go. Let me describe the plans for today. So I want to cover 3 topics. The first one is homomorphisms and isomorphisms. The second one is the direct product of groups. And the third one is classification of finite abelian groups. So I actually want to cover all of them today. So, okay, so let's start from the first one. So homomorphisms and isomorphisms, what are they? So now we know what the group is, but we may produce different groups in different ways, and we want to have some tools to compare different groups. For example, we need a way to say that 2 different constructions are the same. So if we produce a group in one way and we produce another group in a different way, and the result will be the same, then there is no point to distinguish these 2 groups. So we want a way to compare the groups. So, and in order to do that, we need homomorphisms and isomorphisms. So homomorphisms. So what is a homomorphism? So suppose we are given 2 groups, G and H are groups. Now I want to define a homomorphism from G to H. So the definition, a homomorphism from G to H. So as usual, since this is an abstract algebraic definition, I want to present you some data and then pose some axioms. So first, the data. So phi must be a map of sets. So first of all, phi is a map. So it takes elements from the group G to the group H. And it must satisfy one axiom. So it must preserve the operation in the following sense. If we take 2 different, any 2 elements from the group G and multiply them, and then apply the map phi, the result must be the same as we apply the map phi to each element and then take the product. So this is a homomorphism. So in this, so if we are given, so let me repeat. So if we are given 2 groups, G and H, and we are given a map from the set G to the set H such that it satisfies this property, then this map is called a homomorphism from the group G to the group H. So, and just in case, here we have 2 operations, one multiplication here and one multiplication here. The blue one is an operation on G, and the red one is an operation on H. So here we multiply using operation here, and here we multiply using the operation here. Are there any questions? Okay, so let me give you several examples. So examples. Example number 1. So suppose our group G is Z with addition. So let me write it like that. And H is just any group. So I want to produce a homomorphism from Z to H. In order to do that, I fix an element in H, just any element. And then I define a map which takes an arbitrary integer k to kth power of the element H. So this is a map phi. Well, it depends on H, but I'm not going to put any indices here. So this map is an example of a homomorphism from Z to an arbitrary group H. So we just take an element, an integer k to a kth power of an arbitrary element H, and this element H is fixed for this phi. And actually, any homomorphism from Z to an arbitrary group has this way, looks like that. And in this case, H is equal to phi of 1. So H is the image of the generator for this cyclic group. That's an example number 1. Are there any questions regarding this example? By the way, so I presented a map here, but why this map is a homomorphism? Why does it satisfy this axiom? Well, actually, this axiom means that if we multiply 2 powers, then the exponents of the power, we need to add the exponents of the powers. So we already proved that. Example number 2, if we take the group of permutations Sn, and H is the set of plus minus 1 with, and the operation is multiplication, then we have natural map with a sign from G to H, which takes any permutation to its sign. And we know that the sign of products of permutations equals the product of signs. So this means that this map is a homomorphism. And the third example, you already know, if G is GLN of R, which is the group of all invertible matrices of order n with multiplication, and H is R star, which is the set of all non-zero scalars with multiplication, then the determinant which is a map taking A to a determinant of A is a homomorphism, which means that the determinant of the product of matrices is just the product of the determinants. So these are examples of homomorphisms. Okay.
Excuse me, and what is R star?
Oh, okay. R star, so as a set, this is the set of all real numbers without zero, and the operation is multiplication. So this is basically GL1 of R.
Oh, okay, thanks.
Sir, can I show the axiom again, please?
Yeah, let me show you the axiom. So you take 2 elements from the left-hand side, you apply the operation from the group G, and then apply your map. On the right-hand side, you apply the map first and then multiply the results using the operation from the second group. And these two must be the same. Okay?
Fine.
Okay. So now I want to make several remarks regarding homomorphisms. So let me formulate a claim. So if phi is a homomorphism of groups, then first, it takes the identity element of the group G to the identity element of the group H. And second, it takes inverse element of G to the inverse element of phi of G for any G from G capital. These are two properties of any homomorphism. So by the definition, homomorphism must preserve the operation, but then it automatically preserves the identity element, which is the neutral element of the groups, and it preserves the inverse elements. This is how it works. So let me prove this. The first one. Well, we know that this holds in G because the identity element must satisfy this property. Now, let's apply phi to this equality. Then we get phi of 1 equals phi of 1 times 1, which is phi of 1 times phi of 1. And we have this equals this. But now, all these elements, they live in the group H. And in the group H, each element is invertible by the definition of the group. So we may multiply this equality by phi of 1 inverse, just multiply it, say from the left, and then we will get 1 equals phi of 1 in H. That's it. That's what we want. Are there any questions? Okay, so let me proceed. The second one, we want to show that phi preserves the inverse element. So let's take an arbitrary element G from G capital. And we know that G times G inverse equals 1 in the group G. Let me apply phi to this equality. We will get phi of G times G inverse equals phi of 1. But we already know that phi of 1 is actually 1, the neutral element of H. And since phi is homomorphism, this is the product of these two elements. So we have this final equality, that this is equal to this. So now I want to multiply by phi of G inverse on the left. So I want to cancel this, and it goes to the right hand side. So after this multiplication, we will get phi of G inverse equals phi of G to the power of -1. And this is exactly what we wanted to prove. And that's it. Let me show you the whole proof. So the claim was that any homomorphism preserves the identity, and any homomorphism preserves the inverse element. Are there any questions? Okay, so now I want to give you the second definition for today, which is the definition of an isomorphism. So the homomorphism is a way to compare two groups, but if we want to say that two groups are the same we want the notion of an isomorphism. So again, let G and H be groups. The definition. I want to define an isomorphism from G to H. So again, what kind of data do we have? So phi must be a homomorphism. Phi from G to H is a homomorphism. And what kind of axioms do we have? Well, phi must be bijective. So it's one-to-one correspondence between elements of the groups. So let me formulate this in a different way. So what does it mean that we have an isomorphism between two groups? Well, formally, this means that we have a bijective homomorphism. But what is this? So let me show you a picture. So first of all, what does it mean that we have a bijection between two sets? So suppose we have two sets, a set X and a set Y, and we have a bijection.
They are equivalent. We know this from discrete math course.
What again?
They are equivalent.
Yeah, but just give me a second. So a bijection means that each element here has a unique element here. So like we have this one-to-one correspondence. But how should you think about this? So you may think that X is a set of names for your elements. For example, you may have like X consists of A, B, and C. And Y is a different set of names for your elements, which is 1, 2, and 3. And your bijection, say, takes A to 1, B to 2, and C to 3. Then you may think of it as like this is just a way to rename the elements. So here you have names A, B, C, and here you have names 1, 2, 3. But A and 1 is actually exactly the same element. B and 2 is exactly the same element. But now, but here it has name B, and here it has name 2, and the same for the element C. So the bijection is just the way to rename all the elements. This is how you may think about the bijection, any bijection. So, these two sets are essentially the same, but the elements have different names. And now, if in addition these two guys are groups, what does it mean? That you have an isomorphism. So if now G and H are groups and phi is an isomorphism, well, first of all, it's a bijection, so we may think that G and H are exactly the same sets, but the elements here have different names. And what does it mean that it's also a homomorphism? Well, it means that if you take an element here and an element here, and you compute their products, and you get an element here, and then takes it here. Or you may do it in a different way. You may take an image of each element and get the results, and then multiply them here. And the result will be the same. So this simply means that the operation on G remains the same when you rename all the elements. So isomorphism means that you rename all the elements and you switch the notation for the operation, but the set is exactly the same set, and the operation is exactly the same. The only difference are the names for the element and the notation for the operation. That's how you should think about the isomorphism. We had notion of bijection, of course, of discrete. Yeah, okay, I know that you know what the bijection is, but I want to clarify the way you should think about the bijection, because usually mathematicians describe the formal notion, but it's very important to understand how you should think about all this formalism. So, well, let me just repeat what was going on here. So what I was trying to explain, that if you have an isomorphism from the group G to a group H, it simply means that you have exactly the same group. So G and H are exactly the same. And the map phi just renames the elements from G and maps them to the elements of H. And it just takes the operation from G and it converts it to an operation on H. So, but the group is exactly the same. That's how you should think about an isomorphism. Okay, so let me give you several. If you have any questions, please ask. But now I want to give you several examples. Example number 1. So let's take G to be the group Zn with addition, and H to be the group mu n, which is the set of all complex numbers with this condition. This is the set of all complex roots of order n. And here, suppose that psi, yeah, in a sense they're equal, yeah. So they're not the same sets, like here, the sets A, B, C, and 1, 2, 3, they are different sets. They consist of different elements, but they are not literally this. They are not literally equal, but they are the same. They, well, essentially they are the same. So this is the notion of a bijection, but isomorphism extends this to the case of the groups. Yeah, they're equal, but not literally. Exactly, and that's how you should think of it. So they have exactly the same properties. So if you change a group to an isomorphic one, you change nothing. So if it's more convenient to switch a group to an isomorphic one, just do it, because you don't change anything. So suppose that psi is primitive root. I'm sorry for my handwriting, primitive root. So then we can produce this map, which takes a remainder k to the kth power of the primitive root. And this is a bijection which preserves an operation. It takes an addition, the addition from Zn to multiplication in mu n. So this is the group of all roots of order n, and this is the group of all remainders modulo n. And this is an example of an isomorphism. So that's one example. Now, a second example, you may take a group Z and with addition, of course. And you may take a group of matrices of this form where n is an integer and the operation is multiplication. And then you have a map from here to here, which takes an integer k to a matrix of the form. And this is also an isomorphism. Well, I'm not going to check all the axioms. I want to provide, well, several examples for you to look at them later if you need them. And also the third example, if G is a cyclic group, we already know that we have two options. If the order of the element G is infinite, then all powers of G are different. And if the order of G is equal to n, then we have like n distinct powers and they repeat in cycles. But now, since we know the notion of an isomorphism, this simply means that if order of G is infinite, then G is isomorphic to Z, and the isomorphism is provided by this map. And if order of G is finite and is equal to n, then our cyclic group is, well, I forgot to mention that this is the notation for an isomorphism. When I want to say that, when I want to clarify that some homomorphism is an isomorphism, I just write this tilde over the arrow. So when I say that this is an isomorphism, well, I mean, this notation is exactly equivalent to saying that this homomorphism is an isomorphism. So in the second case, if the order of the element is n, then G is isomorphic to Zn, and the isomorphism is given exactly by the same rule. The remainder k goes to the element G to the k. So there are only two possible situations here for a cyclic group. It's either Z or the group of all reminders modulo n. So this is why these two groups are important, because they describe all possible cyclic groups up to isomorphism. So there are no other cyclic groups. So if you are given a cyclic group of order n, you may assume immediately that this group is Zn. That's it. And by the way, these two isomorphisms are not unique. For example, you may switch a generator. So I can change G, for example, to G inverse. And this gives me a different isomorphism of G to Z. So this isomorphism is not unique. So, okay, let me show you all the examples just in case. If you have any questions now, please ask. Okay, so now each homomorphism has two additional groups related to it. So if we have a homomorphism from a group G to a group H, then we may define the kernel of phi and the image of phi. What is the kernel of phi? Kernel of phi is the set of all elements from G going to the identity element in H. So the kernel, the kernel is a subgroup here on the left-hand side. It's a subset of G. And the image of phi is the set of all elements of the form phi of G, where G goes through all the elements of G capital. So this is just a set theoretical image of the map phi, and the image is a subgroup here in H. Okay, so now I want to formulate several properties of these groups and explain why they're, by the way, I forgot to mention. So these are some subsets. So kernel of phi is a subset here, and image of phi is a subset here. But now I want to prove that these guys are subgroups and show some other properties of these subgroups. So do you have any questions regarding the definitions? Okay, so let me formulate the claim with the properties. the claim, if phi is a homomorphism of groups, then there are four properties. The first one, the kernel is always a normal subgroup. Normal subgroup. Second, the image is always a subgroup. The third property, phi is surjective if and only if the image of phi is equal to H. Well,
Excuse me,
this is
is the image of H a normal subgroup?
no, the image of phi is not necessarily a normal subgroup. There are a lot of examples where an image is not normal. The kernel is always normal, but the image is not necessary. So the third one says that phi is surjective and only if the image is H. Well, the Captain Obvious was here and told me that I should formulate this property. And the last one, phi is injective, and this is the interesting one, if and only if the kernel of phi consists of the identity element only. So these are four properties of the kernel and the image. So they are the kernel and the image, they are subgroups. The kernel additionally is a normal subgroup. And then you may check surjectivity and injectivity using image and kernel. Well, surjectivity is equivalent to image being equal to H, and injectivity is equivalent to kernel being equal to the trivial subgroup consisting of the identity element only. So this is how it was in linear algebra. If you want to check that a linear map is injective, it's enough to check that its kernel consists of 0. That's some analogy from the linear algebra. Do you have any questions regarding this claim? Okay, let me show you how it works. Well, the first one, the kernel. So it's a subset in G. What do we need to check that it's a subgroup? We need to check that the identity element is in kernel. If we have two elements A and B in kernel, then the product is in kernel. And the third one, if we have an element A in kernel, we need to show that it.
Can I ask? I missed the point. Is it we are formulating it for a homomorphism? Yeah.
What again?
We are formulating these properties for homomorphism. Yeah.
Initially, we are given a homomorphism phi from G to H. Yeah.
Yep.
Because if phi is just an arbitrary map, well, it doesn't make sense to define the kernel and the image. Well, you may define them, but the kernel may be empty, and they are just arbitrary subsets. It's not an interesting case. It's like dealing with nonlinear maps in linear algebra is not an interesting thing. So here, phi is always a homomorphism from one group to another group. So, and now we want, in order to check that kernel is a subgroup, we want to check all these three properties. But in order to check this, well, how do you check that something belongs to a kernel? You just need to show that phi takes these elements to the identity element. But we know that the identity element goes to the identity element that was proven before. So the one is true. The second one, we know that A and B, each element A and B goes to the identity element. So we want to prove that their product goes to the identity element. But since phi is a homomorphism, then phi of AB is phi of A, phi of B. And since each of these guys is 1, so the result is also 1. So that's why we preserve the product. And the third property, so if we know that phi of A is equal to 1, then we want to check that phi of A inverse is equal to 1. But we know that a homomorphism preserves the inverse element. Now we know that phi of A is 1, so it's just 1 to the power of -1, and this is again 1. So this shows that AB and A inverse also belong to the kernel, so it satisfies all the properties of a subgroup. Are there any questions?
Yep, I have a question about third and fourth property, not about this exactly, but about fourth and third property. We have been told that G phi is a homomorphism from G to H, and then we consider that phi is injective and surjective, but this is they should follow from homomorphism because phi is bijection.
No, isomorphism is a bijection. There are two notions, a homomorphism and an isomorphism. Homomorphism is an arbitrary map preserving an operation, and isomorphism is a bijection preserving an operation. Let me show you.
Okay, I got it. Thank you.
Yeah, okay, well, no problem, yeah. So yeah, your homomorphism is an isomorphism if and only if the image is equal to H and the kernel is equal to the trivial subgroup. Okay, are there any other questions? Okay, so now how do we check that kernel is a normal subgroup? Let me recall that in order to check that, we want to show that for any element G in our group G kernel phi G inverse is a subset of the kernel phi. So what does it mean? It means that if I take an arbitrary element H from the kernel, then the element GH G inverse must be in the kernel. But let's check. So how do you check that something is inside the kernel? You just apply phi to this element and you want to show that the result is 1. So now since phi is a homomorphism, you do this. Since H in the kernel, this element is 1, so this is phi of J, phi of J. Let's write it like that because we know that phi preserves the inverse element, and now these two elements cancel each other, so the result is 1. So this computation check this embedding, so this means that the kernel is a normal subgroup. Okay, I want to skip the proof of the second one because it's done exactly in a similar way. The proof will be written, and it's actually already written in the notes. I will share them after the lecture. And I want to skip the third one, but let's discuss the proof of the third one, and then I will prove the fourth one. But before we switch, do you have any questions regarding the proof of the first property? So it consists of two steps. The first step, we check that it's a subgroup, and the second step, we check that it's normal. Okay, so the third one must be obvious. It's just the definition, it's just by definition. So the image is the set of all elements coming from G. So the surjectivity means that the image equals to H, so this is just some reformulation in this form. So it's not something interesting. So the interesting part is injectivity. So phi is injective if and only if kernel consists of the element 1. So let me show you this. Oops. So the first property. So we have this map from G to H. So suppose that phi is injective. We need to show that the kernel contains only one element, the identity. Well, we know that the identity must be inside the kernel because phi takes 1 to 1. So by definition, y1 is inside the kernel. And suppose that there is any other element in the kernel. But then it simply means that these two elements, like 1 and g, they goes to the same element 1. But since phi was injective, it simply means that g is equal to 1. So there are no other elements in the kernel except the identity element. So this was this implication. Injectivity implies that the kernel consists of one element. Are there any questions? Should I repeat? Okay, so the other way. So now we know that the kernel consists of the neutral element only. And I want to show that if I take two elements, G1 and G2, in the group G, and if their images are the same, then it implies that they are the same. So this is what we want. And this is what we are given. Okay, let me show you. So we know that the images are the same. Let's multiply these by phi G2 inverse, let's say on the right. Then we will get phi G1, phi G2 inverse is equal 1. Is equal to 1. But now we know that phi preserves the image, the inverse. So this is the same as this. Now, since phi is a homomorphism, this implies that we have this. And this means that the element G1, G2 inverse is in the kernel. Oh, that there was not enough space here. Oops, my bad. Let me redo that. Now I know how to do this. Let me put it here, and also I'll put it here, and I delete this. Yay! New technology. How good? How impressive is that?
Very cool.
Yep. So so now we know that G1, G2 inverse is in the kernel, but this means that G1, G2 inverse is equal to 1 because the kernel consists of one element only, and now we multiply by G2 on the right, and we will get what we need. And that's how the proof works. So just go here, and the result is what we need. Are there any questions? Yeah, the usual whiteboard is strictly limited. You cannot like take a part of a whiteboard and move it to a different part. Okay, unless you need to move the whole piece of the whiteboard and it's movable, but it's not as flexible as this one. Okay, if you have any questions, please ask. If not, then I want to switch to a different topic. I want to discuss direct product of groups. So now we more or less discussed everything we need to know about homomorphisms, examples of homomorphisms, how to compute them. We will discuss during the seminar session. So now let's switch to direct products. Direct products. So this is R, this is I. what is direct product? So, well, we want a way to produce new groups. We don't want to produce groups from scratch. It's inconvenient. It's very convenient to find some operation to produce a new group if we're already given some other groups. And there are a lot of different operations to produce a new group in algebra. And I want to explain one of the simplest ones, which is a direct product. So suppose we're given two groups, G and H are groups. So in order to produce a group, I must give you the data required for the new group and check all the axioms for this data. So if you remember, what kind of data should I provide? I should give you a set and an operation. So the set is the Cartesian product of two sets. So this will be the set for the direct product. And now I want to show you the operation here. What is the operation here? The operation is a rule of this form. Well, it takes a pair G1, H1 and another pair G2, H2 and compute a third pair, which is called the product. And the rule is this: you just multiply G1 and G2 and separately multiply H1 and H2. This is how you compute the product. So let me write it down here. So G1, H1 times G2, H2, but here must be a comma, is equal to G1, G2, comma, H1, H2. So you just apply the operation coordinate-wise. So this is how it works, but you need to preserve the order of the argument. So if G1 was on the left, then here is also on the left. So let me mark it like that. So this is how you multiply the elements. All first elements goes to the first coordinate and the second elements goes to the second coordinate. So this set with this operation is called the direct product of the group G and H. So this is the direct product. Let me direct product. Or just product. Now, I need to show, well, actually, I've given you some data, like a set and an operation. Now, I have to check three axioms because it may happen that this is not a group. The operation may be like awful, who knows? So we have to check the axioms. So what are the axioms? We need to show that the operation is associative. We need to show that it has identity. There exists identity. And we should show that there for each element there is an inverse element. Well, in order to check that the operation is associative, we just need to multiply three elements in two different ways, and direct computations shows that the operation is associative. I'll skip it here, but the corresponding computation will be in the lecture notes. But let me show you what the identity here is. So the identity is just a pair consisting of two identity elements. So this is the identity in G times H. Because if you multiply by this element on the left or on the right, you don't change the other element. You can see it from the rule here. And if you want to compute the inverse element for GH, you just compute the inverse element coordinate-wise. So you can check that if you multiply GH by this pair on the left or on the right, the result will be this pair, which is the identity element here. So this element satisfies the definition of the inverse element. So it's simple. Well, this is more or less all you need to know about the direct product. It's just the definition of a group. Let me just recall that just by definition, a direct product is just a Cartesian product of two sets with the coordinate-wise operation, and the identity element is just this thing, and the inverse element for each pair is this thing. And that's it. Are there any questions here? Okay. Now, one additional notation. If we're given several groups like G1, G2, etc., Gn, we may define a direct product of this family in a similar way. This is just a Cartesian product of all these sets, and the operation is a coordinate-wise. Then the identity is just a tuple with all identities here, and the inverse is computed in exactly the same way. So I believe that everyone can extend the definition to the case of several factors. So I'm not going to waste my time doing that. Okay, and now I want to switch to the last topic for today's lecture, which is finite abelian groups. Well, this is one of the most important classes of groups in algebra, and we want to know everything about them. So finite abelian groups. By the way, how is the pace of the lecture? Is it too quick today, or is it okay?
It's okay, I believe.
Yeah, I think it's pretty okay.
Okay, if you have any problems with the pace, just tell me. It's okay if I slow down. I mean, there is no need to rush. My goal is to explain everything. Well, I'm trying to be quick to not because I don't want to waste my and your time. So, okay. So finite abelian groups. Well, the definition is. Well, the term is self-explanatory. What is a finite abelian group? Well, a finite abelian group is a group which is abelian and finite, which means it's commutative and has finitely many elements. But let me just write it down. So G is finite abelian group if it's commutative so the order of the operation doesn't matter, and it has finitely many elements. That's it. That's what means that G is a finite abelian group. Okay. Now, let me formulate one of the most important claims here. Claim. Let G be a finite abelian group. Then it's isomorphic to a group of the form like this. So every finite abelian group is isomorphic to a direct product of finite cyclic groups. There are no other finite abelian groups. Like every finite abelian group is a direct product of cyclic groups. That's it. That's the whole story. I'm not going to prove this because we don't have the required technique. And actually, even if we, even if I start proving this, probably it will be a waste of time because, the proof doesn't contain any interesting ideas. It's just a direct computation. So it doesn't help you to learn anything about finite abelian groups, except some tricks and how algebraists use these tricks when they want to prove something like that. So I hope, yeah, Ilya?
Can you repeat, please, what is FAG?
Finite abelian group.
Oh, thank you very much.
Yeah, it's just for convenience in order to save my time and your time. Acronyms are very useful when you need to save your time. Okay, so let me show you several examples because it's very important to understand several things. So a finite abelian group may be given in a very sophisticated form. For example, you may define G as Z8 star with multiplication. Let me recall that Z8 star means that we take all reminders modulo 8 which are co-prime with 8. So here it means that we take all odd integers from 1 to 7, and the operation is multiplication modulo 8. So how many elements are here?
8,
No,
7.
no,
14.
4.
4.
0 is not co-prime to, you're null star, okay, yeah.
So these are all elements of Z8,
Yeah.
all the reminders.
Yeah.
Now we want to cross out all the elements which are has factor 2. 0, 2, 4, and 6 are the candidates for going out. So 1, 3, 5, and 7 are co-prime with 8. And now the operation is multiplication. So if you, for example, take 3 times 5 modulo 8, it equals 7. If you take 5 times 7 modulo 8, it equals 3, and so on. If you take 3 times 3, it equals 1 modulo 8. And so this is a finite abelian group, but it's not presented in this way, in this form. You see, it's given like a set and an operation, but we know it must have this form. So let me show you. Oh, oops, wrong color. So there are 4 elements. So so G consists of 1, 3, 5, and 7. Well, the claim is that Z8 star is isomorphic to Z2 times Z2. And let me show you the bijection here. So we have 4 elements here: 1, 3, 5, and 7. So 1 corresponds to the element 0, 0. 3 corresponds to the element 1, 0. 5 corresponds to the element 0, 1. And 7 corresponds to the element 1, 1. You may check that this map actually preserves the operation, and it's obviously a bijection. So this is an isomorphism. I'm not going to waste my time to check that this map preserves the operation, but it's a nice exercise. So this is an isomorphism. Okay. So by the way, this is not the only one possible isomorphism here. I could define an isomorphism using a different set of rules. I could take these elements to, well, the identity must go to 0, 0 in any case. Well, I could take 3 to 0, 1 and 5 to 1, 0, but this is not very interesting because it corresponds to changing the order of these 2 factors. But what is more interesting that you could do this: 1, 0 7 goes to 0, 1, and then 5 goes to 1, 1. This is also an isomorphism. And actually, all possible isomorphisms here look like that. You take any two elements from the set of 3, 5, and 7, and take one of them to the element 1, 0, take another one to the element 0, 1, and the third one goes automatically to the element 1, 1. And these are all possible isomorphisms between this guy and this guy. So you see, this was a finite abelian group, and it was not obvious, well, what was the structure of this group? I mean, how it looks like, I mean, how to deal with this group. But now, because we know this classification result, we know that it must have this form, like it must be a product of cyclic groups. And here we explicitly describe how to present this group in this form. So that was the first example. Do you have any questions regarding the example? Okay. In
And what's the
particular,
operation on Z2 times Z2?
oh, it's addition. I mean, when I so how to well, how to recognize the operation? So if you take Z2, the operation is always addition. Okay. It's just like always Z and Zn, they always have the addition as an operation, because multiplication doesn't provide you with this group structure. But now, when I take the product, the operation is inherited from the operation of the factor. So if it was addition here and addition here, then on the direct product, you use addition for the first coordinate and addition for the second coordinate. That was exactly what was told here. Okay? So the operation is inherited. So here is addition, and on the direct product is a component-wise addition. Okay. Are there any other questions?
Excuse me, can I please ask a question? How do we find this like mappings? For example, how do we know that 1 maps to 0, 0? Yeah, like by Cartesian product rule, we just like multiply.
So your question is, how did I find this isomorphism?
Yes, I mean, how to
well, I have some tools which are not acceptable for you. So that's the first answer. And the second answer, this is just, let's say it's a call to a God, to the God. Just, hi God, could you tell me how should I map all those elements? Oh, you say 1 goes to 0, 0, okay. Then 3 goes to 1, okay. And then 5 goes to, and so on. So yeah, just the God help.
Okay, thank you.
That's how it works. But actually, the reason was I just know some tools, and these tools, well, these tools are more advanced. We are not prepared to discuss them, but we will study some simpler situations. So for now, I just want you to to see the exact mapping between the elements. And now, since you know the map, you can check that it satisfies the definition of a homomorphism.
Okay, thank you.
Mm-hmm. Are there any other questions? So best you with nice. Okay. Let me show you the second example. The second example was is Z9 star with multiplication. And in this case, so this is also the set of all elements, the set of all reminders, module 9, coprime with 9. And here it happens that this group is isomorphic to Z6, so it's cyclic. So in the previous example, Z8 was not star, was not cyclic, and this group is cyclic. And actually, the isomorphism goes like this. There are two different isomorphisms. The remainder K goes to the to the kth power of an element 2, or you may find a different isomorphism here where the remainder k goes to kth power of the element 5. Well, I'm not going to add more details here. I just want to provide you with this example and show you several differences. So here, Z8 star is not cyclic and Z9 star is cyclic. So this is the first difference. Also, in both cases, this isomorphism is not unique. There are many ways to identify this guy with this one, and there are actually 2 ways to identify this guy with this one. So, okay, now I want to show you, one main tool in this, regarding finite abelian groups. It's called the Chinese remainder theorem. So the Chinese Chinese remainder theorem. So suppose we are given two coprime integers. Well, suppose they're even positive. So m and n are 2 positive integers and they are coprime. Then a map from Zmn to the product of Zm and Zn given by the rule k, the remainder k goes to the pair k modular m, and here k modular n. So this map is an isomorphism. So this is the Chinese remainder theorem. So this group is isomorphic to this group via this map. So are there any questions regarding the claim of the result? Oh, I'm sorry. Just one. Okay. Now, let me, by the way, did you prove this during the discrete math course?
Yes, we did.
So, but did you prove this in this form?
Not in number theory, I believe.
By the way, okay, do you think, well, let me reformulate the question. Should I prove this?
Yes, please.
Okay, that's good. So first of all, so now we have what? We have a map from Zmn to Zm times Zn. And we want to show that this is an isomorphism. What do we need to show? First of all, we need to show that this is a homomorphism, so it preserves the operation. So first of all, we need that phi is a homomorphism. Second, we want to show that this map is injective. And the third one, we need to show that this map is surjective. So then it will be a bijection. So in order to show that it's a homomorphism, we need to show that it preserves the operation. What does it mean? It means that if we take an element from Zmn, k1 and k2, 2 elements, then phi of k1 plus k2 is equal to phi of k1 plus phi of k2. So here the operation is Zmn, and here the operation is Zm times Zn. Okay? But let me recall the definition of the left-hand side. So this is what we want to check. What was the definition of the left-hand side? It was like K1 plus K2 modular M and K1 plus K2 modular N. Okay, that's the left-hand side. What is the right-hand side? The right-hand side is K1 modular M, K1 modular N, plus K1 or K2 modular M, K2 modular N. And this plus in the middle is the notation for the operation on the direct product. So just component-wise addition in the corresponding group. So now we want to show that this equals this, but this is the same to show that this is the same as this plus this modular M, but that's exactly what's written here. And again, we need to show that this is the same as this plus this modular N, but this is exactly what's written here. So these two things are the same. So is it clear, or do you have any questions? Okay. So now we know that this is a homomorphism. Now, I want to show you that this map is injective. The second thing, phi is injective. In order to do that, I want to compute its kernel. What is the kernel by definition? It's the set of all reminders such that phi of k is equal to 0, 0. But what is phi of k? Phi of k is a pair k modular m, k modular n. This is the definition of phi of k. And when is it equal to 0, 0? Well, exactly when m divides k and n divides k. So these two conditions means that the element k belongs to the kernel of phi. So let me rewrite it here. So the kernel of phi is equal to all the reminders in Zmn such that m divides k and n divides k. But now, since m and n are co-prime, this is exactly the same as all reminders here, such that the product divides k. But since k is an element from 0 to mn minus 1, the only option here is k equal to 0. And that's it. The kernel consists of the 0 element only. So we know that it's injective. So let me show you the whole proof. Are there any questions regarding the proof? Okay, and now I want to show you the surjectivity. And it's really simple now, because the third one, phi, is surjective. Okay, I have 8 minutes. I believe I have enough. So I want to formulate one claim also. So now let us compute the amount of elements on the left-hand side. It's just m times n. Now I want to compute the amount of elements on the right-hand side. So since this is the Cartesian product, the amount of elements here is just the amount of elements in the first factor times the amount of elements in the second factor. So this is just Zm times the amount of elements in Zn, which is m times n, which is exactly the same number as here. So these two groups have the same, exactly the same number of elements. And phi is an injective map from this guy to this guy. So it's injective. And these two sets have the same amount of elements. But then it automatically means that phi is surjective. And that's it. Okay, So if there are any questions, please ask. I just want to show you the whole proof and recall the claim. So the claim was that this group is exactly the same thing as this group. And here was the proof. And this is the exact map from the left-hand side to the right-hand side. It's very convenient to know how the inverse map looks like. So when we want to go back, if we are given a pair A and B, how to produce an element here, we will discuss it during this seminar session. But now I want to make one remark regarding this claim. So as we can see, that Z6 is isomorphic to Z2 times Z3 using this theorem. So this group, Z2 times Z3, it doesn't look like a cyclic group because it's a direct product of two cyclic groups. But by the Chinese remainder theorem, it's actually a cyclic group. And from the other example, like Z2 times Z2, well, this is not a cyclic group. This is not Z4. Why? Because all elements here have order 2 or 1. And so there is no generator, there is no element of order 4 here. So this group is not cyclic. So sometimes this product can be simplified to one cyclic group, and sometimes it cannot be simplified to just one cyclic group. This is the remark I wanted to mention. And now I want to formulate one final claim. So why do I need it? So you see that, well, because of this Chinese remainder theorem, we may write our finite abelian group in different forms, like this form or this form. If we have a lot of multiples here, like there are many options to write down our finite abelian group. And it's very hard to tell, are these abelian groups the same or not? For example, if I take something like Z10 times Z3 or Z5 times Z6, are they isomorphic or not? So, well, we need something to do in order to answer this question. So in order to simplify our task, I want to formulate the claim which answers precisely this question: how to check if two products of cyclic groups are the same or not. So the claim. So suppose G is a finite abelian group. Then it's uniquely presentable in two different forms. So, there is unique presentation of G in the form Z D1 times etc. times Z dk, where D1 divides D2 divides D3 etc. divides dk. So that's the first claim. So all these numbers are greater than 0. So if you can represent your finite abelian group in this form, like a direct product of cyclic groups such that the order of this group divides the order of the next one, and so on, then this form is unique for the group G. So if you have two groups presented in such form, then they are isomorphic if and only if they have exactly the same form, like here. And the second claim, we have a unique presentation of the group G in the form Z P1 K1 times etc. Z PR KR, where PI are prime numbers, not necessarily distinct ones. So they may repeat R prime. So, okay, So every finite abelian group uniquely presentable is either in this form or this form. In this case, we have this condition, the order of one group divide the order of the next one. And in this case, we have this condition that the order is just the power of a prime number. And prime numbers may repeat here. Well, do you have any questions regarding the claim? Is it clear what I'm saying here?
And what is z p1 times k1?
I mean, this is the index. So p1 to the power of k1, it's a number.
Oh, it's
so
to the power, yeah. Sure,
yeah,
okay.
it's
okay.
inside. Yeah, it's like the name of the index. So let me show you several examples. So suppose we are given two groups, G, which is Z2 times Z6, and H, which is Z12. In this case, G and H are presented in the first form, because you see, here we have cyclic groups and 2 divides 6. And here we have only one factor, so the condition is empty. So, and we see that these and these presentations are different. So this automatically means that these groups are not isomorphic. So there is no isomorphism between G and H. These are different groups. This is how you use this claim. Or you may use the Chinese remainder theorem, and then the group G is isomorphic to Z2 times, and Z6 is isomorphic to Z2 times Z3. So now you present the group G as a direct product of cyclic groups, and the order of each cyclic group is a power of a prime number. Here is the first power of 2, then the first power of 2, and the first power of 3. And you see 2 and 2, they may repeat here. And in the second case, if you apply H, the Chinese remainder theorem to the group H, then 12 is a product of 3 and 4, they are co-prime. So this is Z4 times Z3, which is Z2 to the power of 2 times Z3. And also here, you present your group H in the second form. Every cyclic group has order, which is a power of a prime number. And you see this form and this form, they are different. So here we have 2 factors with Z2 and Z2, and here we have just one factor, Z2 to the power of 2. So this explains that G and H are not isomorphic using the second presentation. Okay, I see we are running out of time. We already have -2 minutes. So if you have any questions, please ask. If not, then thank you for being here. And I hope it was at least fun and probably even useful.
Thank you.
Thank
Okay,
you.
thank you guys.
Yeah.
Thank you.
See you next
Goodbye.
time.